Okay, recording now.
All right. Thank you all for letting me speak again. It's very gracious of you. Um, a lot of the slides that I'm going to show were taken from a talk that Masahiko gave in Banff. Some of their slides are older than that. And of course, uh, it's a bit like cleaning out the refrigerator and just putting slides together and hoping that it's digestible. Now, maybe I need to be in full screen mode. Let's see. How's that?
It's good.
Fine.
Okay. Yeah, all right. So some of the work was done while I was an international research fellow in Japan, supported by JSTS. Seiichi Kamada contributed to some things, and I was at ICERM in the fall. The talk will include work from recent collaborations with Victoria Lebed, Seiichi, Bjori Kim, and Sung Yang, as well as Masahiko, older work with Masahiko, and of course, CJKLS is me, Dan Jolzowski, Seiichi Kamada, Laurel Langford, and Masahiko Saito. Masahiko had a slide which had about 25 people on it, 23 people on it. And alphabetically, I think we missed one or two letters in the alphabet. But let's carry on. So I want to start out with this picture. This is a broken surface diagram of the two twist spun trefoil. And it's a broken surface diagram that has a triple point here. There's one here. There's one here. And there's one here. So in addition to the broken surface diagram, I've tried to describe a movie. Our artist friend Nancy Hawking suggested that I put this in a perspective drawing. And so the movies get flipped over and under or front and back as you move from top to bottom. But there's a sequence of movies, each between the stills, certain critical events are occurring. And this diagram was proposed by Sato and Shima. They used quandle 3 cocycles to show that the minimal triple point number for a projection of the two twist spun trefoil is 4. They constructed an image of the double point set. In a way, gave a diagram of such a projection that's available on YouTube, and it's absolutely beautiful. And then Kawamura gave a movie of this, which was highly symmetric. And from Kawamura's movie, I was able to draw the image above. I should also say that the two twist spun trefoil is example 12 in Fox's quick trip in knot theory. And at that Georgia conference, Sir Christopher Zeman was present. But when it occurred to me to ask the question whether he had been inspired for twist spinning by Fox's talk, he was too ill at that point to respond to the question. So twist spinning came about a bit later, but the first example of such a knotted surface was given by Fox as example 12, and I guess a sequence of examples of that form, which Kanenobu showed, were all twist spins. So let me review. A quandle is a set with a binary operation. It will alternately be denoted by star or triangle, and we'll say that A is acting upon A from the right. For every B and C, there's a unique A such that B acted upon by A is C. For every A, B, and C, self-distributivity holds. And so examples of quandles are the dihedral quandle, where you take Z minus N and you take 2B minus A. You can take a group say A star B, or A acted upon by B is B conjugated A. You take an automorphism of an abelian group and take TA plus 1 minus TB. That's called an Alexander quandle. And then the analyzed Alexander quandles where A acted upon by B is T of the quantity AB inverse type. All of these examples were known to both Joyce and Matveyev. Some of them were known to Takasaki. So the quandle axioms correspond to Reidemeister moves and not colorings. In this case, what you do is you stand along the over arc, looking in the direction of the orientation of the over arc, and hold out your left hand. I know that I don't need an orientation for the under arc, but in this case, I did put an orientation in the under arc. So if it's a negative crossing, then your left hand will be pointing towards A acted upon by B. If it's an overcrossing, then your left hand still will be pointing towards A acted upon by B, okay? And then the axioms correspond to the Reidemeister moves. A acted upon by A is A. If you can't read the fonts, I can magnify them, but I think you're probably familiar with these things. I've just given up trying getting the indices correct on the Reidemeister type 2 move. So I just lay down A and B, and then the unique element that you get is on that short bit of undercrossing arc. And of course, self-distributivity is what happens when you follow the thoroughly undercrossing arc to the end on either side of the Reidemeister move. Sam, you look like you have a question.
Not at this time. It's very interesting.
Okay. I'm just recalling the definition of a quandle, and later on I'm going to use the word shelf. So a shelf is a set for which only the type 3 move holds. A rack is 2 and 3, and a spindle is type 1 and 3. And that the last bit of fanciful terminology is due to crayons and Baez and crayons. So self-distributivity is called the shelf axiom.
Can you explain why it's the shelf axiom?
Yes. So you have a rack, which is 2 things. And if you replace, so if a rack is something that you place objects on, a spindle is how you build a rack. So 1 and 3 is a spindle, and shelf is analogous to a rack. That was their joke when they were working this out. And spindle is a what do you call it? It has assonance with quandle or something. So
it's at least a real word.
Yeah, shelf is a real word. Rack is a real word. Spindle is a real word.
My objection to quandle is there's a made-up word.
Yeah. Yes, and I point this out in the next slide. David Joyce coined the word quandle, which has no meaning in English, and he was a student of Peter Fried, and there was. I think at the time they were talking about quantiles of some sort, so that's probably what got him into the word. If the quandle is involutory, so there's an inverse operation defined by the second axiom. If the quandle is involutory, it's also called a K, and those were introduced by Takasaki in Manchuria in 1942 or 43, Matveyev was talking in the USSR about 1978, and Joyce's dissertation appears to be completely independent, well, around 1979. But Matveyev's paper didn't appear until 82. Brieskorn used the word automorphic set, and the 3 of you used the word racks. Okay, so I want to briefly remind you of what the fundamental quandle looks like. So we look at homotopy classes of maps. The maps have their base point upon the tubular neighborhood. Sorry, they start at the tubular neighborhood. There's a base point, which later on we'll put on the tubular neighborhood. And then homotopies are required to stay at the top. They're required to stay at the base point, and they're required to stay along the boundary of the tubular neighborhood. Otherwise, they're free to move about. And if you look at a crossing dead on from the point of view of the overarc, then the left-hand underarc may be colored A. The right-hand underarc would be colored C. And then that C is the same thing as A acted upon by B because there's an explicit homotopy given by the keyhole picture. Okay, so the way that one constructs quandles is to start out with a group, look at its automorphism group, and then define, fix an automorphism, or for a fixed automorphism, define A acted upon by B via phi by the formula A B inverse. You apply phi to A B inverse and then multiply that by B in the group. Here the automorphisms are going to act on the right. I find that a little bit more convenient for this. And there are 4 properties that hold here. Certainly, and they're easy to verify. Certainly A acted upon by A via phi is going to be A because you see there's going to be an A here. And so that's going to be phi of the identity, that'll be 1, and this will also be an A. If phi is the identity, then there's nothing there, and so the B's cancel. And then if you have 2 different automorphisms, you just check and see that the action determined by phi, and where B is acting and then B is acting subsequently via psi, gives you the same thing as if A were acted upon by B by the composition of phi. And then the 4th version of this is this strange conjugation that happens in the middle. These are not 4 girlfriends. They're called group families of quandles. We'll come back to that in just a moment. But so you actually have a whole family of quandles for any automorphism, for all the automorphisms here. But if you fix the automorphism, then you indeed get a quandle on the underlying set of the group. The construction is due to Joyce and Medvedev. They didn't axiomatize this. This was axiomatized quite a bit later. And it was axiomatized by Ishii, Iwakari, Jang, and Oshiro. And the point is that if you have a group and acting upon a set, and you have a collection of binary operations that satisfy these axioms, then you get a G family of quandles. And from a G family of quandles, you can construct a quandle. It's a little bit like a group extension, but not entirely like a group extension. I should also mention in GF3, Shatitsky noticed that if you had a set with and looked at all the binary operations on the set, then you could put a monoid structure on the collection of binary operations, and the monoid structure would be given by GF2 and GF3. So that's kind of cool. Okay, so we use quandles to color, not diagrams. So if we color the arcs in the diagram, and the set of quandle colorings don't depend on the diagram. You get the same colorings before and after the Reidemeister moves, and the number of colorings is a non-invariant. And it's a very powerful non-invariant. So I want to look at this Reidemeister type 3 move for a moment. Here we've put in all the labels as indicated, and now we're going to start putting in a subsequent label. So we're going to define a function, phi AB. It's a function of 2 quandle variables. And the way it's shown at this crossing is that there is a source under region and then the overarc. And so this will be labeled phi of AB. This one will be labeled phi of A acted upon by B, comma C. This one will be labeled phi BC because you see those are on the sources. This one will be phi BC. This one will be phi AC, and this will be phi A acted upon by B, B acted upon by C. And so if you have a function which takes values in the abelian group, it's a quandle cocycle if it satisfies this first condition, it's a rack cocycle. And the second condition is that it phi of x comma x is 0. So the rack homology was defined by you folks, and then we imposed this other condition to give quandle homology. And strangely enough, I have notebooks from Warsaw in 1995. I've almost obliterated all of my notebooks and old notes, but this one I preserved. And Brian spoke about this on August 8th in 1995, and he talked about immersions covered by embedding and homotopy groups of rack spaces. He mentioned Jennifer Flowers' thesis in this and showed I guess there are a number of people that are involved in this. Colin, Raj, Brian, somebody named Green, Jen Flowers started looking at the homotopy classes of maps of the rack space. And Nosaka has made quite a good industry of that in recent times. So if we have a quandle cocycle, so the quandle cocycle phi takes values in an abelian group A, X is a quandle, then we can form X cross A, and we can put a quandle structure like that on that pair of elements. It's a bit like a fiber bundle, so you put X is acted upon by Y, and A is then translated by the cocycle phi of XY. And this defines a quandle structure on E if and only if the function phi of XY is a quandle cocycle. In contrast, when you have a group, an abelian group, a group cocycle would satisfy these two conditions. If you have an identity in either argument, the cocycle is 1, and then it satisfies this condition, which is a bit arcane, but we'll come back to it. And then two group cocycles are cohomologous if they differ by this quantity, where gamma is a function from G to A. Okay, yeah.
Could you go back on that slide? I was just wondering why the right-hand side of that equation doesn't involve B.
That's a good question, because it doesn't need to. There are other types of extensions where you mix everything up. Those were defined by Andruskiewicz and Grania. I think when we noticed this, we just tried a variety of things until we got a formula that worked. But yeah, that is curious. This is one of my favorite quandles. It's a 4-element tetrahedral quandle. And this is the quandle table. It's described by labeling the vertices of a tetrahedron 0 through 3. And then the quandle action is to rotate the remaining 3 elements through an axis that goes through a vertex and pierces the opposite face. And you rotate in a right-handed rule with respect to that axis. And that gives you the quandle table. The reason it's one of my favorite quandles is that I was on a plane to a conference once and tried to color, being very stupid, I tried to color the figure 8 knot with 4 colors. And I succeeded just by looking at, well, 0 acted upon by 1 should be equal to 3. 0 acted upon by 3 should be equal to 2. So you get these 4 conditions. And then you sort of think, well, maybe it should be a magic square, fill it in as a magic square, fill along the diagonal, and then check that it is a quandle. it is indeed a quandle. And yeah, it's a quandle. And what do I want to say about it? I guess it's coming up. So let's look at this tetrahedral quandle. It has a non-trivial cocycle. The cocycle is this function psi over here. It's the not 3 cocycle. So if there's a 3 that appears in the argument, the value is 0. If there's a diagonal, the value is 0. And so it's non-zero on anything that doesn't involve a 3. Then there's an abelian extension of that quandle by this cocycle. And when you write down the quandle table for that abelian extension, you get the quandle Q81, which is in Benjamin's list. And I've forgotten what the geometric description of Q81 is. I'm sure that it has a geometric description. And if you sort of parse this table out into blocks, yeah, so you can see that this 4x4 block is the same as this 4x4 block. These two 4x4 blocks look almost the same, but things are translated around. And so the epimorphism from Q81 to Q41 is just reduce the elements mod 4. Right, so the inner automorphism group of the quandle Q41 is A4. In fact, another way of thinking about Q41 is it's just 3 cycles in A4 given by conjugation. There's a twofold extension, a group extension of A4, which is SL2Z3. This is also the binary tetrahedral group, so it's what you would get using Lou's trick, hanging a tetrahedron from a band from a ceiling and then taking care of the twist in the band. And so the inner automorphism group of Q81 is in fact SL2Z3. One way to see that is you just look and see what the cycle structure is, write down the group that's generated by those cycles, look for certain subgroups, and you realize that it's a group of order 24, and then look in the table of all groups of order 24, and that's what it's got to be. Okay, so Q41 is a coset space of A4, and Q81 is a coset space of SL2Z3, and the group and quandle extensions play nicely together, and I'll tell you a little bit about that. So, right. Let's suppose the quandle is given. Let's suppose the automorphism group acts transitively, and let's pick a Z in the quandle S, and then let zeta correspond to the action of Z, and then let H be the stabilizer of Z, the subgroup of automorphisms that stabilize Z, and then define a quandle structure on the automorphism group by means of this formula. This is just the same formula as Matveyev and Joyce's formula. And then define a evaluation map from the automorphism group to the quandle S just by evaluating any automorphism of Z. And this, since the automorphism group acts transitively, EZ is surjective, and the equalizer is exactly H. And so the Joyce and Matveyev idea is that this quandle S is the same thing as this triple, where you look at cosets of the equalizer and then define an action upon them. More generally, if the quandle doesn't act transitively, then you can break things up into stabilizers and so forth. So getting back to Biori's thesis, how's the font here? Is this okay?
Yeah, we can read it. Can read it.
Yeah, I'm not going to read the entire slide to you, but I want to point out this bit here. if you have a group extension, then you can describe the group extension G tilde in terms of the group G and the abelian. So this is a central extension, the group G and the abelian part group A. And then you can just take you can give a correspondence with the elements of G tilde with pairs of elements in G and A. And then you can define a section so that it's normalized so that the identity goes to the identity. And here we're going to define the section so that zeta goes to zeta 0. And then the cocycle value is given by comparing the two different values of the section. And right, there's some bits about inverses which I'm not going to dwell upon, but if you take this group and an abelian group, you fix an element in G, and you take a group cocycle, then you can define this function here by this horrendous formula, and this is a quandle cocycle. And this is very nice. So she gives this as a lemma in her dissertation, and she says, okay, define this quandle cocycle like this. And the proof that it is a quandle cocycle is an incredibly tedious algebraic computation. It's a bit nicer diagrammatically, but I'm not going to give it here. And then she states as a theorem that this function from group homology to quandle homology is in fact a group homomorphism. So that's quite nice. Okay. So getting back to applications to the knot theory, if X is a quandle, B is a quandle cocycle, then the way you define an invariant for knots is you evaluate the cocycle at the incoming colors at a crossing. If the crossing is negative, then put a sign. So we'll write the coefficient group multiplicatively, put the sign of the crossing here, take the product over all the crossings in the diagram, and then sum over all the colorings, and that's an invariant of the knot. What you've done is you've taken all the colorings of a given knot and you've partitioned them according to how the cocycle value changes. And Masahiko gave this example. By the way, on Masahiko's homepage, there's a plethora of results about the state of the art of quandle cocycles, and I think that this is quite up to date. So if you look at all the knots up to 9 crossings, you get these cocycle values using the abelian group. Z mod 4 is the coefficient group. So let's see. You do have things that have both trivial one value in Z mod 4 and another value of Z mod 4. I guess the interesting, there's one that has all 4 terms there. So there are some knots that have all 4 terms there. I can't give you an attribution to this, but I believe it was due to Edwin Clark and Masahiko Saida. Okay, so this is the picture for a quandle 2 cocycle. So in general, let's define quandle homology. You take the free abelian group generated by n tuples. Right. If we start with a group, then the group homology is defined by the Kyoto bus formula. You pay the bus driver when you get off the front, or you don't get off, or you sit together, 2 people on the same seat in the bus. For the boundary maps for quandle homology, and forgive me if I've attributed this to too many people, it's some subset of FRS there. And you all can tell me which subset it is, but you pay everybody to the left, or you don't get on in the middle is how the boundary map is given. And then to get quandle homology, you divide out by a submodule, which is degenerate, where the two elements, if they're together, so if those two elements are together, then and they're the same quandle element, then you just throw everything out of that form. Okay, so a quandle 3 co-cycle is a function that satisfies these two conditions. We can fool with the formula, but I'd rather fool with the diagram. So I'm going to shadow color the diagram by putting a color A here in the source. All of the normals to the arcs are pointing to the right. And so this region up here would be colored A acted upon by B. This region is colored by A acted upon by C. And then you read region, source region, undercrossing, source undercrossing, and then overcrossing. So you read A, B, C. You read A acted upon by C, B acted upon by C, D. Read A, C, D. On this side, you have A acted upon by B, C, D, A, B, D, and then at the last region, everybody has been acted upon by D. And so that's the 3 co-cycle condition. That's the rack 3 co-cycle condition. To make it a quandle 3 co-cycle, we just assume that if there's a coincidence among successive elements, adjacent elements, then throw the values out. Here's an idea that's due to Lebed and Chatitsky. So you can look at a module upon which a quandle acts, and the module axiom is going to be this. You can also look at if you have a left shelf action, then you have this action. So the description of the module action is given by these two diagrams here, or the left axiom here. And then what they observed is that the way the boundary map works is that so this is a bit like the curtains that Roger and Colin had in their VW vans when they were tooling about Europe, picking up women. And so these are these beaded curtains. And so if you take this bit and you push it in front of everything, then everybody gets acted upon by XI. If you push it in back, I didn't write the action here, but you can actually take the left module action here. And in fact, you can get birack homology by means of that simple formula. In this slide, I just want to outline some of the classical or some of the results. They're actually also knotted surfaces are mentioned here. So just some of the things that quandle co-cycles can do for you. Chirality of the trefoil was detected by 3 co-cycles. Iserman characterized the unknot. So the second homology of the unknot is 0. If you have a knot, then its second homology is Z.
You should put Brian's name on that as well, I think, Scott.
Okay, well, yeah, I don't think he's here, so he'll forgive me.
Yes.
Sorry, Brian. Yeah, okay. And so with Mohammed and Dan Silver and Susan Williams, we showed the non-existence of checkerboard colorings for virtual knots, which is maybe not such a great application. I mean, that's just an aspect of the homology of the abstract knot. We also used Watto's representations to get that the Kashino knot was non-trivial. Masahiko and some of his students discussed tangled embeddings. We can determine what the minimal number of Fox colorings are used. Ishii and Tanaka, Ishii and Iwakiri, Jang and Oshiro gave invariants of handle body knots. Masahiko and Ed Clark studied what happens when you embed the quandles in SU2 and watch how they deform. Inoue and Kabiya showed that the complex volume is a quandle co-cycle invariant. And with Mohammed and Shinsato, we determine the minimal number of type 3 moves that were used to perform certain operations. So, for example, if you want to move the braided picture of the trefoil to the trefoil picture, you need 2 type 3s. If you want to turn the figure 8 knot to its mirror image, you need 3 type 3s. And to turn the whatever length this is into its standard picture, then you need 3 type 3s. We use non-cocycle code chains to do that. Non-invertibility of twist spun knots was done in the original paper. Danny Ruberman had already showed the two twist spun trefoil is non-invertible. But it's very difficult to show this if you take a trivial handle and attach it to the 2 knot, but the cocycle invariant doesn't detect that. Some remarkable work of Sato and Shima, Hatakanaka, Iwakiri, Mohammed and Yoshira discussed the minimal number of triple points. Oshiro and Kamada discussed symmetric quandles, and they were able to use quandle colorings for non-orientable surfaces for symmetric quandles. Iwakiri gave unknotted numbers for knotting surfaces. Sato and Saito showed that there were a minimal broken sheet number, and we also discussed ribbing concordance for certain surface knots using quandle cocycles. All right, this is an obligatory slide which depicts the 7 Roseman moves. Here I owe an incredible debt of gratitude to Lou because after his sabbatical at Iowa, he came back and asked me, what are the movie moves for the Roseman moves? And that sort of took this research project over about 1988, as I recall. Anyway, these are a depiction of the Roseman moves, and the important aspect of them are the type 3 move where you have this nugatory triple point, 2 triple points of opposite signs cancel, and then the quadruple point move, which is highly important in physics. This is the analog of the Yang-Baxter relation here. Okay, so there. Let me remind you group homology one more time. Here I'm going to put this obnoxious token at the front and again call this the Kyoto bus formula because when you get off the front of the bus, you have to pay the bus driver. Of course, in Kyoto, no 2 people would be sitting on the same seat, but you can put them on the same seat, form an alternating sum, or you may not be able to make it onto the bus. And so that's how group homology is defined. I'll talk about the token in a minute. That formula was always arcane to me until somebody told me that you can think about it in terms of simplices. So if you think about a triangle where the edges of the triangle are colored with group elements AB, then the last edge should be colored A times B. And then the boundary of the chain AB is the difference of the colors on the top of the triangle and the color on the bottom of the triangle. If you look at a chain 1, 2, 3, then the boundary of that chain correspond to the vertices on either side of this move, and either side of this move is dual to a tetrahedron. Okay, so I think we're coming back to this slide again. For the third homology, you take the pentagon relation. Think about this as a chain 1, 2, 3, 4, and then compute the boundary of the chain. Well, you see, you make a move 1, 2, 3 to get here. You make a move that involves 1, 2 times 3, and 4 to get to here. And then the move to get from here to here involves 2, 3, and 4. So that's the one side of the cycle condition. The other side is here you first move, I think there's a typo here. Anyway, I'm not going to go through it because I'm pretty sure there's a typo on there. Okay, so that the boundary squared is 0 follows from the associativity axiom. And so in the case of a shelf, how should a differential be defined so that it implies that d squared is 0? Group homology suggests that you should be considering the boundary of a simplex. Quandle coloring suggests that cubes are involved. So let's look at a set that has two operations. And you can think, for example, of a group with conjugation and multiplication, and then they satisfy these four properties: associativity, distributivity of conjugation over multiplication, an exponential law for conjugation, and then self-distributivity for conjugation. That was old notation. Victoria suggests that it's better to call this axiom the H axiom because it's the IH relation. And so we'll just rewrite those as those four axioms there. It's the same slide with just different names: H, Y, I, Y, and J. All right, so there's a ton of information in this slide. And so the first bit is that I want to think about this, the transition from this tree to this tree as a three-chain ABC. The axiom is the associative axiom. So at the bottom here, we have the associative product. And then over here, I want to think about this as a chain AB separated from C. And then the axiom is that AB acted upon by C is this exponential law, as we said. This here is A is separated from B and C together. And the axiom is what we see on the bottom right of the slide. And then here we have individuals A, B, C, and the axiom, the algebraic axiom is here. So associated to the deformations of these trees, I want to associate these four chains. And I'll roughly tell you what the chains are a bit later. The important thing about those properties is that they are what you need in order to study knotted trivalent graphs. Two of them are what you need to study knotted trivalent graphs. Another one is what you need to study handle-body knots. So Ishii showed that these moves are enough to study handle-body knots. Okay, so we have axiom 8. We think about this as a bit of foam. We have axiom yi. We think about it as a bit of foam where the transformation where this y moves through the transverse sheet occurs over here. For the axiom yi, we have a similar thing. And then if y's are dual to triangles and x's are duals to squares, and you dualize this picture, then you get a primitive drawing of a house, and you get the other side of the house. And so this picture is actually dual to a prism. This picture is also dual to a prism. And so we can modify the rack classifying space by inserting prismatic cells in all dimensions, and these are how those prismatic cells are labeled. Okay? So in the previous slide, we had this thing that was dual to a tetrahedron, and here we have these two things are dual to prisms, and these are again the axioms that we had, and then the last situation where this is dual to a cube, and I guess I didn't draw the cube there. Okay, so homologically speaking, we take the group homology as before. We have this thing offset, and then on the offset, I told you I would explain that bus token, paying the bus driver here, pay the bus driver, this L+1 has to act upon everything to its left. So this L+1 acts on everything to its left. And otherwise we have group homology. And then our chains are juxtapositions of expressions like this. And when we compute the boundary of the juxtaposition, we use the Leibniz rule with the property that if we have a single entity, it will either act or not act. And this type of homology theory is analogous to the tensor product of chain complexes. So in fact, you take a tensor product of chain complexes and you look at what's in every degree, and then the homology is occurring like this. But there's this weird action here. And I actually own a copy of Spanier, and I don't see within Spanier him talking about tensor products of chain complexes. But I've since found out that there may be a paper of Eilenberg and McLean, which is probably older than that, which has similar homological formulas. Okay, so going back to this slide, taking the boundaries, I won't belabor this, but the boundary of this chain consists of these vertices. The boundary of this chain consists of these vertices. The left-hand side of the diagram corresponds to those that have negative coefficients. And then the boundary of this quandle chain here is exactly what you would expect, BC minus BC. I didn't mention this earlier, but these two terms cancel. Certainly that was noticed by the British people long, long ago in general. This formula unifies quandle and group homology in this sense here. And taking it to 11, sorry, I have to check the time. Okay, good. We can look at the higher order chains. So we talked about this picture before where it was drawn as a pentagon. Here, I don't have that the same typo as I had. So the boundary of this is correct, is computed correctly. And then that pentagon relation corresponds to looking at a 4-simplex and looking at the boundary of a 4-simplex. So remember that we wanted things to be prismatic. So the start of the next higher prisms are going to be 4 simplices. And then I'd like to zoom into this for a moment and observe that in this, we can either move this arc to the right, or we can move this Y through the transverse sheet. Once we move the arc to the right, then there's only one way to go. Once we move this through the transverse sheet, there's only one way to go. And so this diagram follows through until you get to this picture. It follows through until you get to this picture. And it was a bit of Masihiko's brilliance when we were looking at IIJO to see that we could express the next order homology in terms of these deformations of trees. Now, when I look at them as deformations of trees, I can take the glyphography and compose the glyphography, and then I get this kind of picture. If I look at them in terms of simplices, then I get a tetrahedron times an interval. Here we have the Y move. So this is actually a triangle times a triangle. And if I take the boundary of this chain, it's just read by looking here versus, sorry, looking here versus looking here. In the tree diagram, I'm not the only person who's observed this, but if you look at the double curves for the tree diagram, you see over here the axiom for a Hopf algebra is showing up. So multiplication followed by co-multiplication is the same as co-multiplication being an algebra homomorphism. It's showing up within that diagram. And that was also a bit of what was noticed by Lou and Masahiko and I when we described lattice field theories for four-dimensional TKFTs. Okay, so there's that. This one is what? It's a triangle cross a square. You also have a simplex cross an interval or an interval cross a simplex. A interval cross a triangle cross an interval, which of course is a triangle cross a square. These are what you have to add to the rack complex in order to compute homology as homotopy classes. And then you have interval times triangle. And then my favorite, the quadruple point move, where the quadruple point move is dual to a hypercube. And I want to look at those things from a different point of view, but I want to back up a second. So the four conditions that I wrote down, we know from Lou's talk that the Reidemeister type 3 move corresponds to this abstract tensor relation. So we could write down an abstract tensor relation for the other three moves. And there's a really trivial solution. It's the coloring solution. So you take as a basis for your vector space the elements in a quandle, and then you define these as deltas. You define the y's as being the structure constants of the algebra, where the structure constant says this is 1 if and only if C is equal to A times B, and then you put in structure constants for the X, where this is a coloring condition. So B must be equal to C and D must be A acted upon by C. And then a Schalgebra is a set that satisfies those four axioms. And if your vector space has a Schalgebra basis, then these tensors satisfy these four conditions. The tensors that are defined here satisfy these four conditions. But if you replace these tensors by chains, or sorry, by cocycles, then you can show that these equations are satisfied provided things are satisfy a cocycle condition. So I'm going to wrap up in just a minute. So these Schalgebra 2 cocycle that's assigned to where X is assigned to the crossing, Y is assigned to the trivalent vertices. And so this will remain unchanged under the moves to handle binding knots. Why stop there? Go back to the tree diagrams that I drew for the other things and just think about them as abstract tensors. And you get this marvelous system of 8 equations. Among those is a version of the Zamolodchikov equations. It's quite a queer version of it, but it is nonetheless a version of the tetrahedral equation. And so you can write down these tensor equations. And so you can pretend you're a physicist, write down these tensor equations. Recall that you sum over repeated indices. So here you would sum over D. And I'm not going to go through all of those. And then you can do two things. You can check that the colorings are satisfy a veracity. So you have bases that are Schalgebra elements, and then everything satisfies the appropriate color conditions, or you can assign cocycle values to each of these tensors. So you assign K as a map, W as a map, M as a map, and J as a map. And then you find a solution to these system of equations using the algebra cocycle conditions. And same ideas work at higher dimensions as well. You have a corresponding complex for the algebra, which is this prismatic space. You can add degenerate cells as needed. And that's my story. Thanks.
Sorry, I had to unmute myself, so to speak. Okay. Well, thank you, Scott. That's very interesting. Very interesting. Are there any questions?
As clear as an unmuddied lake, as clear as an azure sky is of deepest blue.
I think I must have missed something. What is Q81? What are these Qs?
Okay, so Vendramin has compiled a table using GAP of various quandles.
Oh,
And so 8.1 happens to be the first 8-element quandle in Vendramin's table. I'm sure that there's a geometric interpretation of Q81. I doubt that it's just sticking to stellating the tetrahedron, but I bet it's related to stellating the tetrahedron.
okay. And Vendramin has a list, does he? Of these?
Yeah, he's compiled an incredibly long list of quandles with maybe up to about 30 or 40 elements.
That's on his website, is it?
I think you can link to it from Masahiko's website. Vendramin, I'll put.
It'd be good to have a reference.
I'll type the name in chat.
Hi, Bri.
Hello.
Yes, Brian. Sorry, I neglected your name at one point in one of the slides.
That's okay.
Okay, so that's that would be how you spell it, Benjamin. He's Argentinian. He was a student of either Grania or of Andruskiewicz. I forget which.
So if I put Vendramin into Google, it would come up.
Benjamin Gap quandle, you'll probably find it.
Probably find it. Okay.
I can do that now if you like.
Well.
One of his papers is on Masahiko's page, or there's a link to it there, so we'll put that in.
Okay, that's good. I hope that comes out in the recording. Yeah. Right. Okay. Are there any other questions?
Just a reminder to have Scott send us his slides.
Yes. Yes. Okay.
What's happening on Tuesday next?
I think Lou is giving a talk.
That's right. I'm talking about Cavana homology.
Cavana homology. Excellent. And then on Friday, I understand Lorenzo is going to give a talk.
I think I might like a little more time to get ready than just a week.
Okay.
I'll tell you when I'm actually ready.
Yeah. All right.
I'm glad you're interested. I had offered to talk about the Guritz matrix, which is a very old invariant and
Sure. Yeah.
has very interesting and actually rather complicated theory associated with it. So, if you don't mind, Roger, I'd like to take.
No,
a
no,
look.
no. It's
We
fine.
don't mind.
Yeah, yeah. We can delay things.
Can you tell us about the relation between the Gertz matrix and coloring, or do you know this?
So the relationship between the Gertz matrix and coloring is simply that the Gertz matrix is essentially an Alexander matrix with the variables set equal to -1.
Ah,
So since the Fox colorings involve setting the variable from the Alexander polynomial to -1, you can detect Fox colorings with the Gertz matrix. But I mean, that is not very subtle. So that's very direct.
yeah, okay.
Excellent. Are there any volunteers for next Friday? Don't all rush. Well, we might have to have a holiday. But we'll see. Somebody might pop up with an idea. Okay, so I will stop recording now and look forward to seeing you all on Tuesday.